67, that's it. Okay, stoichiometric calculations. So again, I feel like this follows better when we talk about this moles to mass to everything conversion. Moving into stoichiometry actually kind of makes more sense, and then hopefully I'll be able to come back to that stuff in the middle. If not, that's what will be on the video assignment that I will post, okay? Okay, so hopefully you guys watched those videos from last Thursday and you know how to balance chemical equations. You also should know all the information that a chemical equation gives you, right? So what is the first thing that chemical equations tell you about a chemical reaction? What's actually reacting, right? What is the chemical formulas of our reactants and products? What else does it tell you? The physical state, right? So we always list the physical state in parentheses, depending on what you're looking at. What else does it tell you? Most importantly, when we balance it particularly, the actual numbers of things that are going to be reacting, right? So this reaction, we have octane. This is what the CHH18 molecule is. This is octane. Who is it reacting with? Oxygen. What is it forming? CO2 and water, right? What type of reaction is this? Combustion reaction, okay? So note that this is balanced. And when it is balanced, what it's telling you is the actual relative numbers of molecules that are reacting in the overall reaction, right? What this tells you is that for every 2 of these octane molecules, you are going to produce 16 CO2s and 18 H2Os, okay? So the balanced chemical reaction gives you a lot of information. It tells you the actual numerical relationships between the reactants and the products, okay? What we call this, these numbers in front, this is what we call the stoichiometric coefficients, and overall, these various numerical relationships is what we call reaction stoichiometry, okay? So this is a funny little word, stoichiometry. I use it quite frequently though, so be aware of what I'm meaning when I say stoichiometric coefficients or reaction stoichiometry. Okay, so now, chemical reactions, right? Chemical reactions are a lot like cooking, okay? So we're going to utilize a little analogy to try to explain what I mean by stoichiometry. So if you want to make something, you have to have a recipe, right? So let's say you want to make a pizza. What do you need to make a pizza? What's number 1? Crust, right? Let's say you want it to be cheese pizza, nothing else, right? So what else do you need? You need some sauce, okay? And then you also need some cheese, okay? So let's say that we went in and we looked up a recipe for pizza. And in that recipe, we needed crust, we needed sauce, and we needed cheese, okay? So for this chemical reaction, what are our reactants? The crust, the sauce, and the cheese, right? Also what is given in a recipe is the actual amount of things that you need, right? This tells you that in a recipe, you need 1 crust for every 5 ounces of tomato sauce and every 2 cups of cheese. What is going to be the product in this chemical reaction? Pizza. So these guys are all going to combine, and how many pizzas are you going to make out of this? Just 1, right? So if we wrote this as a chemical equation, it would look something like this, where we have these numerical relationships as if they were little stoichiometric coefficients in our reaction, okay? So for every 1 crust and 5 ounces of tomato sauce, 2 cups of cheese, you make 1 pizza, okay? Okay, so we're going to continue with this. So now, let's say that we have 6 cups of cheese. How many pizzas can we make? 3, right? So you guys just mentally did that, but what did you utilize in converting between cups of cheese and pizzas? You utilize these numerical relationships, right? You utilize the fact that you need 2 cups of cheese to make 1 pizza. If you have 6 cups of cheese, then you can make 3 pizzas. How did you actually get that 6 to 3? What did you do with these numbers in particular? You divided by 2, right? You took your 6, which is what you had, you divided by the numerical relationship to give you overall numbers, okay? So again, if we have 6 cups of cheese, and we're going to write this as some sort of dimensional analysis type problem, if our 6 cups of cheese were on top, and I wanted to convert to numbers of pizzas, what would I put in the denominator here? My relationship, right? For every 2 cups of cheese, I get 1 pizza. When I multiply, these guys cancel, and I end up with 3 pizzas. It's going to be the exact same thing for the other reactants, right? It's going to be the same thing for crust. If I have 3 crusts, how many pizzas can I make? 3, right? Because it's for every 1 crust, I get 1 pizza. If I had 25 ounces of tomato sauce, how many pizzas could I make? 5, right? So we're going to utilize this numbers in our balanced chemical equation just like we utilize the numbers in that recipe. Okay, they're the exact same thing. So what this is telling you, if we go back to our balanced chemical equation for octane, is that for every 2 molecules of octane, how many molecules of CO2 do I get? 16, right? So this is exactly what the balanced chemical equation is telling you. These relative numbers of things, given how many reactants you have, how many products you can produce, right? For every 2 molecules of octane, how many waters will I make? 18, okay? So now, let's utilize that in the same format. What if I had 22 moles of octane? Could I predict how many CO2s, or how many moles of CO2 I would make? So note that molecules and moles are synonymous, okay? They can be used interchangeably because, again, all that is a conversion factor. So what this says is for every 2 molecules of octane, that can also be a conversion between 2 moles of octane, giving me 16 moles of CO2, okay? So now, if I have 22 moles of octane, how many moles of CO2? Can I figure that out given my balanced chemical reaction? Yes, I can, right? What is the relationship? How many moles of octane do I utilize in this reaction? 2, right? So if I have 22 moles to start with, same thing like we did for the cheese, if I had 6 cups, how many pizzas can I make? If I have 22 things to start with, for every 2 of these, how many CO2s do I get? 16, right? All I'm utilizing is the numbers in front of the 2 things that I'm looking at. So if I have 22, for every 2, I get 16. Overall, how many moles of CO2 am I going to produce? 176 moles of CO2. Could I do the exact same thing to determine how many molecules or moles of water I make? Yes, right? Could I also figure out how much oxygen I use in the process? Yes, okay? Now, the problem with this is, do you have a machine that measures moles? Have you been in the lab? Have you looked at anything that looks at moles at all? No, what do we actually measure most of the time? Mass, right? So what is that going to do, right? If we can only measure things in mass, we're going to have to add in another step. What is that step going to be? Converting from grams, right, to what? Moles. Once we're in moles, we can again utilize these numbers that are in the balanced chemical equation, right? But we have to get to moles first. What do you think we're going to have to try to come out of, right? You think we're going to want to end our problem in answering something in moles of CO2? Because again, we can't measure that. What are we probably going to have to do to get out of this problem? Again, convert to grams of CO2 as well. Adds in 2 extra steps with respect to what we were showing you before, okay? So usually you'll be given a mass of something. In determining how much product you actually produce or how much reactant you actually utilize, the first step is converting to moles of that thing. What is going to be the conversion factor between mass of something and moles of something? How did we convert from mass to moles before? The molar mass of the thing, right? So in conversion from grams to moles, we're going to utilize the molar mass. Once we're in moles, then we can use the numbers in the balanced chemical equation. This is what I call stoichiometry land, right? But we have to be in stoichiometry land before we can utilize those numbers, okay? And then finally, after we've been in stoichiometry land, how do we come out of it to convert to mass of whatever we're looking for? Again, conversion between moles and mass is what? Molar mass. Okay, so let's utilize a problem to illustrate this. Okay, so going back to this reaction that we've been looking at, this octane combusting, okay, we're going to use octane as kind of an idea behind just general petroleum, okay, so general gasoline. So in 2010, the world burned 2.5 times 10 to the 15th grams of petroleum. Again, petroleum is just going to be synonymous with our octane molecule that we've already been looking at, C8H18. So the question is, if we burn this much petroleum in this combustion reaction, how much CO2 have we produced in this time frame? Can we answer that? Yes, yeah. We have mass of petroleum, or we have mass of octane, right? We know the relationship between how much octane is utilized and how much CO2 is produced in moles. And can we figure out what the molar mass of CO2 is? Yes, right? We just add up the atomic masses of carbon and 2 oxygens. So let's go through this problem to demonstrate how you would do this, right? So we are starting with 3.5 times 10 to the 15th grams of C8H18, okay? We want to figure out how much CO2 we have produced when we combust all of this octane, okay? Again, we cannot use those relationships in the balanced chemical equation until we are in moles, right? So how am I going to take my mass of octane and convert to moles of octane? Right, so I'm going to take my molar mass, which, lucky for us, they've already calculated for us. So the molar mass, or the molecular weight of octane, is 114 grams per mole. I'm going to take my big 3.5 times 10 to the 15th grams, and I'm going to divide by the molar mass of octane. So it's 114.22 grams for every 1 mole of octane. So that's going to get me into moles of octane. Go ahead and stop there and put this 3.06 times 10 to the 13th moles of C8H18. So now that I am in moles of my reactant, I am in stoichiometry land. So now I can utilize those numbers in front of the balanced chemical equation. What was the numerical relationship between octane and CO2? How many octanes did I use? How many CO2s did I produce? 2 for every what? 16, right? So now that I'm in moles, I can go ahead and convert to moles of CO2, because for every 2 moles of octane, I make 16 moles of CO2. So I'm going to go ahead and scroll over. This is going to leave me in moles of CO2, which ends up being 2.545 times 10 to the 14th moles CO2. Write this back down here, 2.45 times 10 to the 14th moles of CO2. So what was this purpose of this question? We combusted a bunch of octane, we had a mass of it, and I want to figure out what? Mass of CO2 that was produced in this overall combustion, right? So we now have determined the number of moles of CO2 that were produced, but how do I get back out to mass of CO2? Right, so I'm going to multiply by the molar mass for CO2. Again, nice and lucky that somebody's already calculated the molar mass for CO2. This is 44 grams per mole. So we'll go ahead and take that guy. For every 1 mole of CO2, I get 44.01 grams. And that leaves me with a bunch of CO2, 1.08 times 10 to the 16th grams of CO2. So the mole land, stoichiometry land, whatever you want to call it, you've got to get to it by converting to moles first, and then you've got to come out, again, by using molar mass, converting back to grams. Okay, so we're going to try one of these on our own. Let me know when you guys are good with this slide. Yes?
To do a problem like this, we would need the balanced equation at the beginning.
Yes, you have to have the balanced chemical equation, because again, that's giving you the actual numbers of things that react and that are produced. Okay, so are we good before I move on? Question 310. So we have this milk of magnesia reaction. So when you eat milk of magnesia, it ends up being just magnesium hydroxide. it reacts with HCl that's in your stomach, 2 HCl's, to produce water and magnesium chloride, okay? So this reaction is already balanced for you. You don't have to worry about it. What I'm asking is if I ingest 3.26 grams of this magnesium hydroxide, how much HCl is it going to neutralize, right? So how much HCl is it going to react with? And specifically, I want HCl in grams, okay? So exact same thing. You have a reactant, you have a mass of it. To be able to utilize these relationships, these numerical relationships, you have to convert to moles. Then you can figure out, for every one of these, I use 2 of these. To get out of that, you then have to convert back out to grams, okay? So let's go ahead and try this. Okay, I'm going to go ahead and go through this one. So again, if you guys haven't gotten an answer, attempted to get an answer, pause it and then come back to the answer, but I'm going to go ahead and start talking about this. All right, so reaction stoichiometry helps us essentially figure out, given a certain amount of reagent or a certain amount of reactant we have, how much of another reactant we're going to need to completely react with that. It also helps us predict how much product we're going to form, etc. Right? So reaction stoichiometry is super powerful in that respect. Now, the question that we're dealing with here is we have a mass of magnesium hydroxide, right? So we have just said, okay, we've got oops, that's my eraser. Did not want to do that. And there is no going back. Okay, so the question says we have 3.26 grams of magnesium hydroxide, and it wants to know how much HCl we are going to need to completely react with that 3.26 grams of MgOH, okay? Now, we can do that. We can answer that question because essentially that's what these little coefficients tell us in the balanced chemical equation is they tell us for every one of these magnesium hydroxides, we need to utilize 2 HCl's, right? But when they tell us that, they're telling us in terms of molecules, right? So for every 1 molecule of MgOH, we need 2 molecules of HCl. That also converts all the way up to moles, right? So for every 1 mole of MgOH, we need 2 moles of HCl, okay? Now, all of these types of problems are kind of sticky in the fact that they come in masses, right? We can't measure moles in the lab, right? We can only measure masses of things. So the first step for any of these problems is always going to be a conversion step between grams of whatever we're talking about and moles of whatever we're talking about, because we cannot utilize these numbers until we're in moles, okay? All right, so the first step here is going to be conversion of grams of magnesium hydroxide to moles. To do that, we need that conversion factor, which is the molar mass of magnesium hydroxide. To figure out the molar mass of magnesium hydroxides, we have MgOH2. We're going to add up all of the atomic masses of all of the atoms that are in this compound, right? So magnesium, we look up the atomic mass. It has an atomic mass of 24.31. The 2 here goes to both the oxygen as well as the hydrogen. It's distributive, right? So we need 2 times the molar mass of oxygen. That's 2 times 16. And then we also need 2 times the molar mass of hydrogen, which is 2 times 1.008. Right, so we're going to multiply those guys. We're going to add them all together. We end up with a molar mass for magnesium hydroxide of 58. So 58.33 grams per mole. Okay, so again, formula weight, molar mass, molecular weight, they're all numerically equivalent, and we get that from the atomic masses of the elements in the compound. All right, so again, this tells us the mass of 1 mole of our compound, right? We're going to utilize that to take our 3.26 grams of MgOH2, and we're going to convert that to moles. Actually, really quickly, move that down here, and then probably just would have been easier just to erase. But anyway, okay, so again, we've got our mass. We've got our mass here, and we're going to convert to moles using the molar mass. Okay, so Our molar mass says for every 58.33 grams, we get 1 mole. I'm going to take my mass, and to convert to moles, I'm going to divide by the molar mass, right? So the 58.33 grams of MgOH goes on bottom for every 1 mole of MgOH2. Okay, I'm going to take 3.26, I'm going to divide by 58. That is going to give me 0.0559 moles of MgOH. Okay, so that was essentially step number 1. We're taking the mass of whatever reactant we're dealing with and we're converting to moles. Okay, now I'm going to take our 0.0559 moles of MgOH. Now that we're in moles, we can utilize those coefficients in the balanced chemical equation, right? So this tells me for every 1 molecule of magnesium hydroxide, I'm going to use 2 molecules of HCl, right? Another way that we say that is for every 1 mole of magnesium hydroxide, I'm going to use 2 moles of HCl. So if I had 2 magnesium hydroxides, I'd use 4. If I had 3, I'd use 6, right? For every 1, we're going to need 2. So to convert to moles of HCl used, we're going to utilize that exact same ratio, right? So for every 1 mole of MgOH, I need 2 moles of HCl, right? Again, with these railroad tracks, it's whatever we're given is usually, what's going to be on bottom. Whatever we're converting to the desired is going to be on top, right? So essentially, I'm going to take my 0.0559 and I'm going to multiply by 2, right? So that's going to double that, and we end up with 0.112 moles of HCl. Right, so given this amount of magnesium hydroxide, this is the amount of HCl that I need to completely react with that, okay? Now, the problem is this is in moles, and again, we're going to want to come out of this in grams because they're asking for the mass of HCl. So this last little step, we're going to have to take the moles of HCl and convert to grams by utilizing the molar mass of HCl. Right? So for HCl, we have an H, which is 1.008. We have a chlorine, which is 35.45. When we add these guys together, we get a molar mass of 36.458 grams per mole. For every 1 mole, we get 36.458. We're going to take our moles, and to convert to grams, we're going to multiply by the molar mass now. So for every 1 mole of HCl, there are 36.458 grams of HCl. When we take that and we multiply, it ends up with a mass of 4.08 grams of HCl. And that would be the answer to this question. Okay, so again, they're saying we've got 3.26 grams of magnesium hydroxide. What mass of HCl can it completely react with? And that is essentially what we have answered, right? It took multiple steps. It took a conversion of grams to moles step, right? That was step number 1, was conversion of magnesium hydroxide in grams to moles of magnesium hydroxide. Step number 2 took that moles of reactant and converted it to moles of other reactant, right? So reactant 1, reactant 2. We took how many moles of magnesium hydroxide we had. We converted to moles of HCl. And then in step 3, once we had moles of reactant 2, we converted to grams by just utilizing the molar mass of that second reactant. Okay, so hopefully you guys got that one. We'll keep moving on no matter what, okay? So last class, we talked about stoichiometry, right? So we just introduced you guys to the concept of stoichiometric relationships, right? So this is the numerical relationships between reactants and products, right? We also talked about how, well, when we're dealing with these numerical relationships, we always have to be in terms of moles. We have to be in terms of molecules. We can't be looking at this in terms of grams. We talked about how you would go from a gram to a mole and vice versa, from a mole back out to a gram, okay? So now we're going to continue on with that, and we're going to introduce a new little caveat with respect to these stoichiometric relationships, which is called limiting reactants and theoretical yields, okay? All right, so we're going to go back to our little pizza recipe, which is what I introduced you to last time, okay? So we had our recipe, and our recipe was given by our chemical equation. We have 1 crust, 5 ounces of tomato sauce, 2 cups of cheese. That's going to make our 1 pizza, okay? So now let's say that we go to the store, all right, and we buy a bunch of ingredients to make pizza. And what we buy is 4 crusts and 10 cups of cheese and 15 ounces of tomato sauce. And the question is, how many pizzas can we make given this, our starting material for our chemical or pizza making reaction, okay? So how many pizzas can we make? So we'll go through this individually for each of our various ingredients. Oh no. Okay, all right, hold on, stop. Yes, okay. That's not gonna let me move forward. Okay, all right, so we're gonna go through this for each of our various ingredients, okay? So we had 4 crusts, that's what we went to the store and bought. What was the relationship between crusts and amount of pizza that we can make? 1 to 1, right? So for every 1 crust, we can make 1 pizza. So if we have 4 crusts, that means that we can make 4 pizzas, okay? What about the relationship between cups of cheese and pizzas? We went to the store, we bought 10 cups of cheese. How many pizzas can we make? 5, right? Because the numerical relationship is 2 cups of cheese gives us 1 pizza. So in theory, we could make 5 pizzas if we had 10 cups of cheese, okay? So at the very bottom, we only bought 15 ounces of tomato sauce. How many pizzas can we make given that we only bought 15 ounces of tomato sauce? 3, okay? So again, the relationship here is 5 ounces makes 1 pizza. So because of that, we could only make 3 pizzas with 15 ounces of tomato sauce. So given these 3 different starting materials, how many pizzas can we make? 3, right? Once we make 3, we have run out of tomato sauce. And so even though we have excess of the other 2 ingredients, we're limited by our tomato sauce, so we can only make 3 pizzas, okay? In this reaction, this guy is what is called the limiting reagent. So limiting reagent, we also call this limiting reactant. And then this guy, the amount of product that we can make using our limiting reagent is what is called our theoretical yield. In theory, we can make 3 pizzas, okay? Okay, so again, we have our limiting reagent, the reagent that's going to give us the least amount of product, our pizzas, and then the theoretical yield is the maximum number of pizzas we can make given our limiting reagent. The other 2 things are what we call excess reagents, right? So the crust and the cheese, those 2 guys were in excess. There's going to be leftover crust and cheese when we're actually done with this pizza making reaction, okay? All right, so limiting reagent, excess reagent, theoretical yield, okay? So let's say we go in and we make our pizzas, giving our starting materials, okay? And again, we can only make 3, so we go in to make our 3, and as we're pulling one of them out of the oven, we drop it, right? So we drop it on the floor, ruins it, we have to throw it away, okay? So our actual yield in this reaction is only 2 pizzas, okay? So we only make 2 pizzas. In chemistry, we will frequently drop our product or we'll lose it somewhere, okay? So with respect to chemistry, we calculate what is called the percent yield for a reaction because we're not very good at making it given our theoretical yield. So percent yield is calculated as the actual yield divided by the theoretical yield. For this reaction, we made 2 pizzas, but in theory, we should have made 3, right? So our percent yield for this is 2 divided by 3 times 100 because it's a percent, which gives us 67% yield, okay? That should tell you how good you are at actually doing this chemical reaction. Ideally, what should our percent yield be? 100. In theory, we should have made all of the pizzas given our theoretical yield, but we only made 67% of them, so we're not super good at making pizzas, okay? So all of this, our little pizza making analogy is going to apply to chemistry, okay? Instead of pizza, we're going to be dealing with reactants, products. Same type of ideas are going to apply though, right? We're going to have a limiting reagent, we're going to have a theoretical yield, etc. Okay, so again, in moving towards a chemical reaction, most of the time we're going to have multiple various reactants. One of them is going to limit the overall reaction. That is what we call the limiting reagent. The theoretical yield is going to depend on the limiting reagent, and it is defined as the amount of product that our limiting reagent can make. So again, we'll have a theoretical yield. All of the other reactants, all of the other reagents are called our excess reagents, and then we will also be able to calculate a percent yield, given that we'll be provided with an actual yield, what we really make, and we'll be able to compare that to our theoretical yield, what we should have made given our limiting reagent amount, okay? Okay, so we went from pizza. Now we're going to apply this to real chemical reactions, but we're going to start kind of at a little basic state. So we're going to start in terms of molecules, okay? We're not going to deal with masses or moles or anything like that. The chemical reaction that we're going to start looking at is this combustion reaction, where we have methane combining with oxygen to form CO2 and water, okay? And in this combustion reaction, the big trick in most of these is actually just balancing the overall reaction, right? But they've already provided us with the balanced reaction, so we don't have to worry about that, okay? So these numbers in front, right? The methane, the oxygen, the CO2, that is telling you the number of molecules that are actually going to react in this reaction, right? So this tells you that one methane is going to combine with two oxygens. It's going to form one CO2, and it's going to form two waters, okay? So now, let's say that we started with our reagents. We went to the store, and we went and picked up some methane and some oxygen, okay? And we came back, and let's say we had 5 molecules of methane, and we also purchased 8 molecules of oxygen, okay? The question here is, well, how many CO2s, how many little CO2s over here can we make given our 2 starting materials? 5 molecules of methane, 8 molecules of oxygen, okay? So what did we do with respect to the pizza? What did we figure out whenever we had our cups of cheese and our crust? What were we always looking for? How many pizzas we could make, right? Who is our pizza in this type of overall scenario? CO2, right? Our pizza here is CO2. We're asking how many CO2s can we make, okay? So to figure that out, we're going to take our starting material. So we'll start with methane first. We've got 5 molecules of CH4, methane, and we're going to utilize those numerical relationships from the balanced chemical equation, right? So for every 1 methane, how many CO2s do I make? 1, right? Because I have a 1-to-1 relationship. So for every 1 CH4, 1 molecule of CH4, I make 1 molecule of CO2, okay? So again, using dimensional analysis, we cancel out our molecules of CH4, and that tells us that we would make 5 molecules of CO2, given our initial amount of methane, which was 5 molecules, okay? Okay, so in theory, given 5 molecules of methane, we can make 5 molecules of CO2. What about oxygen? So we start with a lot more oxygen, right? We start with 8. So do you think that oxygen is going to be the reagent in excess because we start with so much more of it comparatively? No, right? Because the stoichiometry is important here too. So this is our amount of CO2 that can be produced from the methane. We'll do the exact same thing with respect to the oxygen. So we had 8 molecules of oxygen. So if we have 8 molecules of oxygen, what is the numerical relationship between oxygen and CO2 production? For every 2 molecules of O2, because we have a 2 here, we make 1 molecule of CO2. So in theory, how many molecules of CO2 can I make given that I have 8 O2s? 4, right? So 4 molecules of CO2, which again is our analogy to our pizza, all right? So with the methane, how many CO2s could we have made? 5, right? With the oxygen, how many CO2s can we make? 4, okay? So who is the limiting reagent? Who makes the least amount of product? Oxygen. So oxygen is our limiting reagent or limiting reactant in this reaction, and then therefore, given that oxygen is limiting, what is our theoretical yield of CO2 in molecules? 4. That's how many molecules that we can make given our limiting reagent, or how much product we can make given our limiting reagent. When we make 4 molecules of CO2, we have run out of oxygen. We can no longer do the reaction anymore. So this is what we call our theoretical yield. Okay? So limiting reagent makes the least amount of product in a chemical reaction. Theoretical yield is the amount of product that we can make given the limiting reagent. Okay, it depends on the limiting reagent. Okay, so one more question with respect to this that I'm kind of interested in. So we now know that oxygen is our limiting reagent, right? So our theoretical yield of CO2s is 4. Who's the reagent in excess? Methane, right? CH4. How many initial methanes did we have? We had 5 molecules initially of methane. We know that it is going to be the reagent in excess. Can we figure out how much is left? So how much is left over for our excess reagent? So the answer is yes, we can. And it's going to go back to our theoretical yield, right? So again, when we make 4 CO2s, we have run out of oxygen. We can no longer do the reaction. There's still going to be methane left. How do we figure out how much is going to be left over? So if we have made 4 CO2s, how many methanes did we use in that process? Right, what was the relationship between methane, CH4, and CO2s? And we go back to the balanced chemical equation. It's 1 to 1, right? So if I made 4 CO2s, I know it's 1 CO2 is going to use 1 methane, so that means I used 4 methanes to make this theoretical yield, okay? How many did I start with? 5, so how much is left over? 1, right? So we start with 5. 5 is what we start with. 4 is what we used. So then we'll just take the difference between them. There will be 1 little molecule of poor little methane left over floating in the flask with all of the 4 CO2s. Okay? So it's nice and easy when it's these little molecules and you have to deal with grams and moles and everything else. Okay, so one other thing I want to say before I move on to this, because sometimes the way I present limiting reagents and theoretical yield is I always have you figure out who makes the least amount of product, right? So you always convert to product and then you move forward from there. Another way to do that, though, is to take your 2 starting materials, right? So we had 5 methanes and we had 8 oxygens, and figure out how much you need of each one to completely react with the other, right? So for example, if I was doing it this way, trying to figure out who was my limiting reagent, I would start with my methane, and I would figure out how many oxygen molecules I needed to completely react with my 5 molecules of methane, okay? Again, all I'd be using there is my stoichiometric coefficients. So what is the relationship between methane and oxygen? For every 1 methane I use, I'm going to use 2 oxygen in the process, right? So if I convert this, that means to completely react all of that methane, I would need 10 oxygen molecules. How many do I have? 8, right? So who's the limiting reactant? the oxygen, because again, there's not enough to completely react with the other thing. So that's another way that you could go about answering this question, is figuring out how much of each reagent or how much of each reactant you would need to completely react with the other one, okay? Okay, so let's do a problem. It's not a mathematical problem, it's more of a conceptual one. So we have a flask. It is over here to the left, okay? And in this flask, this reaction is taking place where we have nitrogen and hydrogen combining to make ammonia, and that is a nice balanced chemical equation for this reaction, okay? So in the flask up here, we give you your starting materials, okay? So hydrogen are these little white balls, and nitrogen are these little blue balls, okay? That's the starting material. I want to know, after this reaction has occurred, it's gone to completion, what does the flask look like afterwards? So it could either be A, B, or C, okay? So think about it, talk with your neighbor, and then I'll post this on Socrates.
Okay, so we went over this one in class. So again, for each of these guys, we've got hydrogen molecules in here, right? So hydrogen are our little white balls, and then our nitrogens are our little blue balls here, right? So this is essentially the flask before anything has happened. When they go and they produce their product is ammonia, all right? So this is an NH3, and ammonia is going to look like this, right? The little blue ball is a nitrogen. It has 3 little white balls around it, hydrogen. So this guy is going to represent our little product, our ammonia, okay? So as a note, when we start this reaction, we have 2 of our nitrogen, and then we have 1, 2, 3, 4, 5, 6, 7, 8 of our hydrogen, right? And so now we have to look at the stoichiometry of this reaction. For every 1 of our nitrogens, we're going to utilize 3 hydrogens, and in the process, we're going to make 2 of our products, of our little ammonias, okay? So I can go in and say, okay, so for this guy, this 1 molecule, I'm going to use 1, 2, 3 of this guy, right? For this guy, my little 1 molecule, I'm going to use 1, 2, 3 of the hydrogens. So in that process, I have gone through this reaction twice, right? So if I've gone through this reaction twice, that means that I have made 4 NH3 molecules. I have run out, so this was our limiting reagent here, I've run out of ammonia, but I still have left behind 2 of my little hydrogens, right? So this reaction has proceeded, our limiting reactant was nitrogen, and our excess reagent was hydrogen, and at the same time, we're going to have 4 ammonia. So when I go down here and I look at this guy, in A, we still have a nitrogen left, and we still have 1, 2, 3, 4, 5 hydrogens left. We know that's not the case. We have completely run out of nitrogen, so it can't be A. In B, we have our 4 products, our 4 ammonias, but remember there's still 2 of those white balls left over, the excess reagent, which was hydrogen. Those also need to be represented in our correct flask, right? So it can't be B because that excess reagent isn't there. And so then in C, we get our 1, 2, 3, 4 ammonias, and we get 1, 2 hydrogens. And so this would be the correct answer because, again, in that flask, after this reaction has occurred, we should have 4 ammonia molecules, and we should have 2 hydrogens that are left over.
So now how are we going to deal with a similar type problem where we're starting with initial masses of our 2 reactants, and we're trying to figure out how much product we can produce, again, in terms of mass of the product, okay? So now we're going to be moving from mass to be able to utilize these numerical relationships, our little reaction stoichiometry. We first have to do what if we're dealing initially with masses? We have to convert to moles, right? We have to enter our mole land so that we can actually utilize these numbers in front of the balanced chemical equation. Then we can convert between our various things. And again, to come out, we're also going to have to probably reconvert back out to mass as well, okay? So let's say that we have a reaction where we have magnesium combining with oxygen to form magnesium oxide, right? So what type of reaction would this be? So going back to the brief little reaction types I introduced at the very beginning of the chapter. This isn't combustion technically. Yes. This is a combination reaction, right? We're combining two things into one, and we're getting one thing overall, okay? So, in this reaction, we have 42.5 grams of magnesium. Again, we went to the store, we bought 42.5 grams of magnesium, and we have 33.8 grams of oxygen. So the question is, how much magnesium oxide in grams can we theoretically produce given these two starting materials, okay? So now, the first step in this is going to be taking our two initial masses and converting to moles, okay? First step is always conversion to moles. So, if I wanted to do that, what do I need to do? Right? I have my 42.5 grams of magnesium, I have my 33.8 grams of oxygen, and I want to convert both of them to moles. What should I do? I need to first determine their molar mass, right? So got to look up the molar mass, that's not a big deal. What is the molar mass of magnesium, or how would I figure that out? Just the atomic mass, right? You look on the periodic table, this is just an atom or an element by itself. So magnesium has a molar mass of 24.31 grams per mole. And then oxygen, note that it's O2. So O2, what is the molar mass of O2? Because there's two oxygens. 32, right? This would be 2 times the atomic mass of oxygen, because again, we have two oxygens in the molecule, so this ends up being 32 grams, maybe we'll scroll down, per mole, okay? Okay, so I've got the molar mass for my two starting materials. I am now going to convert both of them to moles. That's my first step. So if I got my 42.5 grams of magnesium, to convert to moles, all I have to do is divide by the molar mass. So this is 24.31 grams for every 1 mole. That'll give me the number of moles of magnesium, which hopefully I have done. Yes. So this is 1.75 moles of magnesium. And then I have to do the exact same thing for oxygen. So oxygen, we have 33.8 grams initially. I'm going to divide by the molar mass for oxygen to convert it to moles. So this is 32.00 grams for every 1 mole. Gives me 1.06 moles of O2. Step number 1, conversion from grams to moles, okay? So now, step number 2, what do you think it's going to be? Right? We want to figure out, given our two starting materials, which are now in moles, how much product we can make. So what are we going to probably need to do? Use the stoichiometry to figure out how much product each of these two guys, in theory, could produce, okay? So we've got our two starting materials. They're now in moles. And we will start with magnesium. So for magnesium, we have 1.75 moles of magnesium. What is the numerical relationship between Mg and our product MgO? 2 to 2, or 1 to 1, right? So for every 2 of these guys, we're going to make 2 of our products. So I'm going to convert my moles of magnesium to moles of MgO using this relationship. So 2 moles of magnesium for every 2 moles of MgO. That is going to give me just the same amount, 1.75 moles of MgO that we could produce given that amount of magnesium. Okay, so that's number 1. Who else do we need to look at? Oxygen, right? We need to figure out, okay, well, how much MgO could we form given this starting material of oxygen? So we're going to take our 1.6 moles of oxygen. Now what is this relationship? How many oxygens do we use in this reaction? 1, so we use 1 mole of O2 because there's a 1 in front. How many MgOs do we make in the process? 2. Okay, so 2 moles of MgO. So I'm going to divide by 1, multiply by 2. That's going to give me a 2.12 moles of MgO. So who's limiting this reaction? Who makes the least amount of product, the magnesium or the oxygen? Magnesium, right? Because it makes only 1.75 moles, whereas oxygen can make 2.12. Okay? So magnesium here is the limiting reactant. That's how you spell reactant. And then what is this 1.75 moles of MgO? So that's our theoretical yield, right? That's how much product we could make given that we have run out of our limiting reactant, okay? But are we going to probably leave this like this, 1.75 moles? No, right? So this is theoretical yield in moles. Write correctly. So this last step is going to be taking our theoretical yield in moles and then converting it back out to grams, okay? So we'll take our theoretical yield. This is 1.75 moles of our product. Could in theory be produced, given that magnesium was limiting. How am I going to convert this to grams of MgO? What is the relationship between moles and grams of something? Molar mass, right? So molar mass of MgO is just the atomic mass of magnesium plus the atomic mass of oxygen. So when I add those two together, I get a molar mass here equal to 40.31 grams per mole. So I have the moles that I have, and I want to convert it to grams. What am I going to do with my molar mass now? I'm going to multiply the moles by the molar mass to get back out to grams, because this is 40.31 grams for every 1 mole of MgO. So our theoretical yield in grams is 70.5 grams of magnesium oxide. Pardon. Okay? Simple-ish, kind of, right? So this is theoretical yield. We'll write this again. Theoretical. Now we're in grams. But again, like I said, we're not very good at making stuff in chemistry, right? So we go into the lab. In theory, we could have made 70.5 grams. But in actuality, we went in, we dropped a bunch of stuff, and we only made 55.9 grams of magnesium oxide, right? So now I'm going to calculate the percent yield for this reaction, which is the actual over the theoretical times 100. So what is our actual yield here? 55.9 over the theoretical, which we just calculated, 70.5 grams times 100. So our percent yield for this reaction ends up being 79.3%. So we're actually better at making magnesium oxide than we were at making pizza, unfortunately. Okay, so that's a lot. I know we're going to do a problem in 1 second. I just have one more little thing I want to hit, okay? And it's this thing right at the end. So now we've calculated who the limiting reagent is. We've calculated the theoretical yield in grams. We've calculated the percent yield, given that we've been given an actual yield. How do we determine how much of the excess reagent is left? So how do we do it with our methanes and our oxygens? What do we have to figure out with respect to the excess reagent? How much we actually used in producing what? Our theoretical yield, our product, right? Okay, so we're going to do that because I promised this would be on the exam. calculating the excess reagent after the reaction is done, okay? So we had our theoretical yield in moles for magnesium oxide. This was 1.75 moles in theory that we could have produced, okay? Now we're going to take this in reverse. We're going to say, how much oxygen do we use in making our theoretical yield in moles, right? So I have 1.75 moles of MgO. What is the relationship again between MgO and oxygen? For every 2 MgOs, we use 1 O2. So I take this guy, I divide by 2. That gives me 0.875 moles of oxygen. Okay, what does this represent? We have made 1.75 moles of magnesium oxide. We've just figured out what? How much oxygen we use to make it, right? So this is what we have used in moles. How much did we start with? 1.06 moles. How would I figure out how much is left over? If I have my starting material and I have how much was used, what's going to be left? What do we do with the methane and the oxygen? We figured out how much we actually used. We had our starting material. What do we do with the two? We subtracted them, right? So to figure out what's left over, I'm going to take how much I initially have. I'm going to subtract how much I use. That's going to give me what is left. So this is used. This is starting. We are left then with 0.185 moles of O2. Again, though, are we probably going to want to leave it like this? No, we'll probably need to convert to grams. So we know the molar mass of oxygen already. That was 32. I'm going to multiply by the molar mass, 32.00 grams. That gives me 5.92 grams of O2 left at the end of the reaction. Okay, so that's great. Let's go ahead and apply it. So I have a question that I want to ask you using all of this information. So we have a bunch of questions here at the end. Actually, that's all I have left is questions for you. So I have one reaction here where we are synthesizing ammonia. The reaction is balanced. We start initially with 86.3 grams of this nitric oxide and 25.6 grams of hydrogen. And I want to know, what is my theoretical yield of NH3 ammonia in grams? So this is on Socrative as a question. Okay, so I'm going to go ahead and go over this problem. So a couple of things that we've set up already. We know that, number one, we're given the balanced chemical equation, right? So for every 2 NOs, we're going to use, so 2 NOs, we're going to use 5 hydrogens. In the process, we're going to make 2 ammonias and 2 waters, right? We also know that we are starting with 86.3 grams of NO, which is nitric oxide, and we're starting with 25.6 grams of hydrogen, okay? And the question that we're asking is, what is going to be our theoretical yield? So our theoretical yield of this guy, ammonia, right? Given that we're starting with that much of NO and that much of hydrogen, okay? Now, the first step in any of these types of problems is, number one, we're going to determine the limiting reagent. So we'll go ahead and write determine the limiting reagent, and I'm going to abbreviate that LR, okay? So that has a couple of different components to it, right? Right now, what we have started with is we've started with masses of our 2 reactants, right? To determine the limiting reagent, we have to figure out how much of this guy we're going to form given our 2 starting materials.
But before we can utilize the stoichiometry in the overall balanced chemical equation, we can't be in masses, we have to be in moles, okay? So the first step, and we'll say this is A, is taking our masses of our two reagents, of our two starting materials, and converting them to moles, right? So that we can utilize the coefficients, the stoichiometry, and the balanced chemical equation, okay? All right, so to do that, we need to take our masses and then convert them to moles utilizing the molar mass of each reactant. So the first thing we're going to need to do is figure that out. How do we figure out the molar mass? So it's just going to be the sum of the atomic masses of each individual atom in the molecule, right? So for NO, this is going to be the atomic mass of nitrogen plus the atomic mass of oxygen. So if I look up nitrogen on the periodic table, it has a atomic mass of 14.01. And again, that's numerically equivalent to its molar mass. I'm going to add to that the same thing for oxygen. So I look on the periodic table for oxygen, it's 16.00. That's going to give me an atomic mass or formula weight of 30.01. And again, that's numerically equivalent to its molar mass in grams per mole. So that's number one. We can do the same thing for hydrogen. So hydrogen is just two individual hydrogen atoms. So all I need to do is add together the atomic mass of two hydrogens. So this ends up being 2 times 0.008, which gives us an atomic mass formula mass or formula weight of 2.016. And again, that's numerically equivalent to its molar mass in grams per mole. Okay, so number one, we need to figure out the molar masses. So here are our molar masses of our two reactants. Now we're going to utilize that and convert our grams for each one to moles of each one, right? So again, we'll start with NO. For NO, I had 86.3 grams of NO. Now I'm going to take my molar mass, and what am I going to do with it overall here, right? So if I have mass and I want to convert to moles, I know for every 30 grams of NO, that's going to get me 1 mole. So it's 30 grams for every 1 mole. I have more than 30 grams overall, but now it's to figure out how many more than 30 grams do I have, right? So I'm going to take my mass, long story short, and I'm going to divide by my molar mass, right? So the grams goes on bottom, so 30.01 grams of NO for every 1 mole. I'm going to take my mass, divide by my molar mass. The grams cancel, and I'm going to be left in moles. And when I do that, I end up with 2.88 moles of NO. And so that's number one. All right, so the other thing we have to do is same thing for hydrogen. So for hydrogen, we had 25.6 grams of hydrogen. We're going to do the same thing. So we're going to take our molar mass, which was 2.016. So we have 2.016 grams of hydrogen for every 1 mole of hydrogen. We're going to divide by that molar mass. And that's going to, again, cancel out the grams. It's going to give us our amount in moles. And this ends up being 5.08 moles of hydrogen. Okay, so step number one, we're going to convert our masses to moles. For our two reactants, we have done that, so we can cross that off. Step number two, which we'll call this B, once we have our reactants in moles, we need to figure out, using the stoichiometry, how much of our product each of those is going to form, okay? So we have NO right now in terms of moles. We have hydrogen in terms of moles. So what I'm going to do now is I'm going to convert this from moles of both of these, so moles of reactant. I'm going to convert it to moles of NH3 that can be produced given our coefficients in the balanced chemical equation. All right, so for nitric oxide, for NO, for every 2 of these guys, I make 2 of these guys, right? So if I had 4 NOs, I would make 4 ammonias. If I had 6 NOs, I would make 6 ammonias, right? If I have 2.8 NOs, then I'm going to make 2.8 ammonias. Again, though, I'm going to go ahead and go through this and convert directly using this stoichiometry. So what this number says is that for every 2 moles of NO, I get 2 moles of NH3, right? So we can utilize those numbers as a unit equation, as whatever you want to consider, to convert to moles of NH3. So note, again, I'm going to divide by what's on bottom. I'm going to multiply by what's on top, and that's going to convert my moles of NO to my moles of NH3. So this gives me 2.88 moles of NH3. And again, I get that by taking this number, dividing by 2, multiplying by 2. I get the same number overall. Okay, so now let's do the same thing for hydrogen. So for hydrogen, we have a different ratio. For every 5, we get 2. So if I add 10, I get 4, etc. So we're going to utilize that. For every 5 moles of hydrogen, I'm going to convert that to 2 moles of NH3. And so when I take 5.08, I divide by 5 and I multiply by 2, that ends up giving me, oh wait, no, you know what, I made a big mistake back here. I'm just going to correct it here because I'm not going to correct it later on. You guys probably were like, what's going on? That's not right. My apologies, this ended up being 12.7 moles of hydrogen. So now when I take 12.7, I divide by 5, I multiply by 2, I will get 5.08 moles of NH3, okay? So second step in this is taking our moles of reactant and converting it to moles of product, right, to figure out which one makes the least, okay? So now we're comparing our potentially 2.88 moles of ammonia to our 5.8 moles of ammonia, right? The limiting reactant is going to make the least amount of product. Comparing these two, this is the least amount, right? So because of that, our NO here, so this guy is our limiting reactant. It limits the amount of product that we can make. And because of that as well, this ends up being our theoretical yield. Let me zoom out a little bit. Yield of product, but now specifically we are in moles, okay? So limiting reactant, it's the thing that we're gonna run out of. It limits the amount of product that we can make. We figure that out by figuring out, given each reactant, how much product they can make. The least amount is our theoretical yield, and that's gonna tell you who the limiting reactant is, okay? Now, in this problem, they wanted, the whole purpose of this was finding the theoretical yield of ammonia, but specifically they wanted it to be in grams, okay? At this point in time, we're almost there, right? We do have our theoretical yield, but it's in moles. So there's one last step to this, and we'll call this, maybe if B was here, we'll call this 2 because we've moved on past the limiting reactant. The last step in this is taking our theoretical yield in moles, and converting it to grams. Okay, so specifically, we have, I'm going to scroll this up, 2.88 moles of ammonia. Now, to convert this to grams, I again need that little, important, I'm at a loss for words for today, but we need our molar mass, essentially, right? Molar mass is going to be that conversion between moles and grams. So we need specifically the molar mass of ammonia. And so to do that, we're just going to go in, we'll say ammonia here. We know it's a nitrogen, and we look up the atomic mass of nitrogen on the periodic table. It's 14.01. It is 3 hydrogens, and each hydrogen is 1.008. So we add all of these guys up, we get a molar mass of 17.034 grams per mole. And so now we're going to utilize that. We have our moles. We want to convert it to grams. So we're going to take the molar mass, and instead of dividing this time for every 1 mole, we get 17.034 grams of ammonia, right? So instead of dividing, when we go from moles to grams, we're going to multiply by the molar mass, okay? So we do that. We take 2.88, we multiply by 17, we end up with a theoretical yield in grams of 49.1 grams of ammonia. Okay, so hopefully you guys got that one. I'm going to do another example problem on the next page. You don't necessarily have to do it if you don't want to, but it is going to get a little bit more difficult because it asks a little bit more difficult of a question. Okay, so I'm going to do this last question. I would go ahead and give this a shot right before you actually listen to the answer. So I'm going to read out the question, I'm going to try to explain it, and then pause it, try to answer, and then come back and see the answer, and I'll go through it. So we have another reaction, right? In this reaction, we're taking nitrogen, we're combining it with hydrogen to form ammonia, right? And again, this is our balanced chemical equation. So for every one nitrogen, we need 3 hydrogens to make 2 ammonias, okay? We've actually already seen this reaction before. This was the reaction that we represented in the little white balls and blue balls question. Okay, so in this question, they're saying, okay, if we start with 5.2 times 10 to the third grams of hydrogen, and we start with 31.5 times 10 to the third grams of nitrogen, what is the theoretical yield of ammonia in grams? So that's part A. And then part B, or in number 2, they actually want to know how much of the excess reagent is left after the reaction is complete, after you've run out of your limiting reagent, okay? So number 1 essentially follows the same line that we were doing in the previous problem, but number 2 is going to throw a little bit of a wrench at you, so make sure you think about it and then try to answer it and then come back for the answer. So if you're going to pause it now, I would pause it now. Okay, so we'll go ahead and start with question number 1. All right, so I'm going to go ahead and rewrite the equation down here. So we've got nitrogen, let's get it to black. We've got nitrogen combining with 3 hydrogen to make 2 ammonia. In the question here, what is our theoretical yield of ammonia if we start with 31.5 times 10 to the third grams of nitrogen, and we start with 5.22 times 10 to the third grams of hydrogen. Okay, so this is going to follow the same exact format, right? To be able to figure out how much of this guy we're going to make, we need to utilize the coefficients that are part of the balanced chemical equation. But before we can utilize those, all of our amounts of stuff have to be in moles, right? These numbers, these coefficients, deal with things in terms of molecules and things in terms of moles. And so the first step in doing this is always going to be conversion. So conversion from masses, which is what we're usually going to be given of our starting material, to moles of our starting material, okay? Again, to do that, we have the mass already that we have of each. We just need the molar mass as that conversion factor that's going to convert our mass to moles. So for nitrogen, to figure out what the molar mass is, so I'm determining the molar mass of all of my reactants right now. For nitrogen, there's 2 nitrogens in that molecule. So the molar mass of that is going to be 2 times the atomic mass of 1 nitrogen, right? So that's 14.01. We would get that from the periodic table. So 2 times 14 is 28.02. And in molar mass, that's in terms of grams per mole. We can do the same thing for hydrogen. Again, we have 2 hydrogens. We just did this one. Each hydrogen is 1.008 grams per mole. So when we multiply these guys, we get 2.016 grams per mole. I'm also going to go ahead and do ammonia because we're going to have to use it eventually anyways. So I'll also determine the molar mass of ammonia down here. So we get 1 nitrogen, which is 14.1, plus 3 times hydrogen, which is 3 times 1.008. That gives us 17.034, and again, that's in grams per mole. Okay, so now for this problem, or the first part of this problem, figuring out what is the theoretical yield of ammonia, we're first going to start with our 2 reactants. All right, so we have their molar masses now. I'm going to take the amount of nitrogen that I have, and I'm going to convert that to moles. So we're starting with, for nitrogen, we're starting with 31.5 times 10 to the third grams. Our molar mass for nitrogen is 28.02 grams for every 1 mole. So I'm going to take my mass, I'm going to divide by the molar mass. And so this is 28.02 grams for every 1 mole of nitrogen. Again, the grams cancel. We're going to be left in units of moles here. So when I do that for nitrogen, I'm going to get confused because I tend to write things just continuously and then I lose track of everything. So we take 31.5 times 10 to the third, we divide by 28. That gives us 1,124 moles of nitrogen. I'm then going to do the exact same thing for hydrogen, right? So hydrogen, we had 5.22 times 10 to the third grams initially. I'm going to take my mass that I have here, I'm going to divide by the molar mass for hydrogen. So this is 2.016 grams for every 1 mole of hydrogen. And so again, grams will cancel and we're left in moles. And for hydrogen, this ends up being 2,589 moles of hydrogen. Okay, so again, this was kind of part A. This was conversion from mass to moles for our reactants. Okay, now in part B, we're going to take the moles of our reactants and we're going to convert to moles of ammonia using those coefficients that are in the balanced chemical formula. Okay, so for nitrogen, if we look back to the balanced chemical formula, for every 1 N2, we make 2 NH3s, right? So we had 2 N2s, 2 nitrogens, we'd make 4, 3 would make 6, right? Whatever we do with respect to nitrogen, we're essentially going to see double of that in terms of ammonia, right? So I'm going to go ahead and write for every 1 mole of nitrogen, that's this guy, what we're converting from, we're going to get 2 moles of NH3. So I'm going to take my 1,124, I'm going to multiply by 2, divide by 1. That's going to give me, in theory, the amount of ammonia that we can make would be 2,248 moles of NH3. Okay, so then that's nitrogen. We also have to do the exact same thing for hydrogen, right? But now hydrogen has a different ratio. For every 3 hydrogens, again, this is coming from this guy, so for every 3 moles of hydrogen, we're going to make 2 moles of ammonia. So when I take 2,589, I divide by 3, I multiply by 2, I end up with 1726, and we're going to get moles of ammonia. Okay, so these are the 2 possibilities, right, given our 2 starting materials. Given the amount of nitrogen that I had, I can make 2,248 moles of ammonia. Given the amount of hydrogen that I had, I can make 1,726 moles, right? 1,726, okay? Again, the limiting reagent is going to be the thing that makes the least amount of product. And between these 2 numbers, this guy, the 1726, is the least amount of product, right? So for this problem, hydrogen is our limiting reagent, right? And this guy, our 1726, this is our theoretical yield in moles. This theoretical yield of nitrogen or ammonia in moles, right? So the last little bit of this, we're going to take this guy and we're going to convert to grams because that's what they want the answer in to part 1, okay? So I'm going to go ahead, I'm going to come back over here. I know this is getting kind of out of control. I'm going to take my 1726 moles of ammonia. And I'm going to utilize that molar mass that we've already calculated, right, to convert to grams. And so I'm going to take my moles. To convert to grams, I'm going to multiply by the molar mass. So for every 1 mole of NH3, we get 17.034 grams. And when I do that, I end up with a large number, so it's 29,400 grams. Again, probably really smart at this point is to convert to kilograms, right? So there are 1,000 grams in every 1 kilogram. And so I'm essentially just going to move the decimal place 1, 2, 3 places to the left. That's going to give me 29.4 kilograms of NH3. And so that is the answer to part 1. Okay, so now we're going to address part 2 because that's kind of the more confusing problem, right? So part 2, they're asking how much remains of the excess reagent. And this is very similar to that little white ball, blue ball problem, right? When we ran out of our limiting reagent, there was still the excess reagent left over, right? And we could figure that out, how many were left over, by figuring out how many we actually used and performing the number of reactions we did, okay? We're gonna do the same thing here, right? We're just gonna have to deal with numbers as opposed to actual like physical balls. But I'm gonna try to explain how you're gonna go about this, okay? So first off, what you're gonna do to figure out how much of this excess reagent remains at the end of this reaction, you're gonna go back to number 1, who is your excess reagent, right? So we knew that hydrogen was limiting. That meant that ammonia up here is our excess. And what we're going to do from there is we're going to say, okay, if this is how much we make, right? We make 1,726 moles of ammonia, and at that point in time we have run out of hydrogen. What we're going to question now is, well, how much nitrogen do we actually use to make that amount of ammonia, okay? So I'm going to start with our theoretical yield. How many products do we actually make in terms of moles? Okay, so we know we make this given our limiting reagent. The question I'm now going to ask is, how many nitrogens do I use to make this amount of ammonia? And so essentially what we're going to do is we're going to kind of be taking this in reverse, right? Again, since we're already in moles, we can utilize those numbers in the balanced chemical equation, right? So if I have 1726 moles of ammonia, for every 2 moles of NH3, how many nitrogens did I use? I would use 1 mole of nitrogen, right? So I'm essentially converting back, right, using those numbers in the balanced chemical equation. So with this, I'm going to take 1726, I'm going to divide by 2, I'm going to multiply by 1, and that's going to convert to moles of nitrogen that I actually use to make this, right? And so when we do that, we end up with 863 moles of nitrogen used once we run out of hydrogen, right? So this reaction starts, we run out of hydrogen. That's actually how much nitrogen that we used to make that amount of ammonia, okay? Now, that is not the same from what we started with, because that's the question, right? If this is how much we use for this reaction to proceed, how much should we start with, right? And so to answer that, we'd go back up here. This was how much nitrogen that was originally put into that flask, right? So this is how much we had initially. Oops, let me do this guy. This is how much we had. This is how much we used. The stuff that's going to be left over is the difference between the two, right? So initially we had 1124. That's what we initially put into that flask. We used only 863 moles of it. This is our used. So the difference is essentially going to be what's left over. And so when we take that difference, we find that we had 261 moles of ammonia left. That's what's remaining in the flask, okay? Now, they don't specify in this what they want this in, right? You could say, well, that's what's left, right? There are 261 moles of nitrogen left over in that flask. A lot of times though, they will specify, okay, how much is left over in grams, right? So finally, with this last little bit, we just need to take the amount left in moles and convert it to the amount left in grams. And again, we'll do that now with the molar mass of nitrogen. So molar mass of nitrogen was up here. For every 1 mole, for nitrogen, for N2, there are 28.02 grams of nitrogen. So we'll take 261, we'll multiply by 28, and so the result of that ends up being 7,300 13 grams of nitrogen left. Lift? Yes, lift. Left. Okay, and again, we can kind of compare that to how much we originally had. Initially, we had 31.5 times 10 to the third grams. This is what we had. This is what is left over. Okay, so again, that type of problem tends to be more difficult. There's a couple more steps involved. You're going to figure out, at least already, you should have figured out what your theoretical yield in moles is. With that, you're going to use that to figure out how much of the excess reagent is used by making that. So that was our step right here. We took the amount of moles of ammonia that we made, we converted back to nitrogen to figure out how much we actually used to make that amount of ammonia. And then to figure out what's left, we had the difference between what we initially entered with versus what we used. That difference is essentially what's going to be left over. And again, if they want that in grams, then you need to take those moles and convert back to grams using the molar mass. Okay, well, that was a long one. Okay, so we've been dealing in this chapter thus far a lot with reaction stoichiometry, right? So we just went over these concepts of stoichiometry, what these numbers in front of our balanced chemical equations, what these coefficients tell us about the amount of reactants that are required, the amount of products that are formed, etc. And in a lot of our problems that we've dealt with thus far, before we can utilize those numbers in the balanced chemical equation, we always have to come in to moles, right? Because again, if it's like a 2-to-1 relationship in our chemical equation, that relates to the numbers of molecules in actual molecules or in moles, right? A lot of times, though, we aren't starting the problem in moles. Instead, we're starting the problem in grams, right? So we'll have a mass of a product or a mass of a reactant. And to figure out how everything relates to that, we first have to convert to moles. So then that we can, once we're in moles, convert to moles of whatever else we want to know. And then we usually have to come out of this in terms of grams again, right? So that's kind of how we've been dealing with all of the problems thus far. We've been given masses of things. We've had to convert to moles. And then once we're in moles, we can utilize those relationships, those numbers that are part of the balanced chemical equation, okay? Again, the way that we relate the mass of a molecule or the mass of a compound to the number of moles it has is the molar mass. And so that's what we've been going over thus far, okay? Now, we're going to kind of switch gears. Because we have talked about other ways that we can relate the amount of something there is, and this is in terms of solution. So if you guys remember, a solution was a homogeneous mixture, right? So it was a mixture, it was uniform throughout, so it was homogeneous, and it consisted of two basic components, right? The first one was what we called the solute. This was our minor component of our mixture. In the second portion, what was called the solvent, this was our major component of our mixture, right? And for solutions that were taking place pretty much entirely in water, our solvent here was water, right? So for all of these guys, our solvent was water, and we gave these kind of a special name. These were called aqueous solutions, okay? All right, so we will have reactions that take place in water. We will have these solution-based reactions. Before we can really talk about those, though, we did also learn how to quantitatively determine the amount of solute relative to solvent in a solution, right? So we had a new unit that we defined. This was called molarity. And this was our measure overall of concentration for these various solutions. Right, so we defined molarity as a big capital M, and it was defined as the number of moles of solute in a solution divided by the total volume of solution. So total volume of solution, and this was in units of liters, okay? So for molarity, Again, it was going to tell us how many particles or how many molecules of solute there were for every liter of solution. Again, majority of the time this was dealing with things that were in water. Okay, so if we are dealing with a reaction that is taking place in solution, and we want to know how much product is going to be formed or how much reactant is going to be needed, again, before we can ever utilize those numbers, we always have to be in moles, except now if we're dealing with solution-based stuff, the way we get to moles is not going to be via molar mass in grams. Instead, it's usually going to be via knowing the concentration of something and the volume of something and utilizing our molarity definition to convert that to moles of whatever thing we want to need, okay? So I'm going to explain what I mean by this in the next slide, in the example. Right, so in this reaction, they tell us that we have a KCl solution, right? So we have 0.15 molar KCl. We have a lead nitrate solution, right? And we know the concentration of it, and we know what volume we have of it, okay? So this overall is our balanced chemical equation for this reaction. So we're over here, this is our balanced chemical equation. And the question that we're asking is, if we know the concentration of our KCl solution, if we know the concentration of our lead nitrate, and we know the volume that we have of it, the question is, what volume of our KCl is going to completely react with this lead nitrate? Okay, so if we want to try to imagine this, we could imagine this guy as having like a nice beaker, right? And let's say that this is our lead nitrate. So PbNO3. We know that there is a volume here that is 0.150 liters. And that volume in milliliters, if we converted that, is about 150 milliliters, just to give you kind of an estimate on the type of volume that we're looking at. And we also know the concentration of the solution is 0.175 molar. So the question we're asking here is, if we have another solution, let's say this is of our KCl, and we know the concentration of it, we know the concentration of it, the question is, what volume do I need to add, right? So what volume do I need to add of it to completely react with my lead nitrate solution, so that there is no more lead nitrate in the solution, there's no more KCl. At this point in time, there would only be product. Okay, so again, to answer these types of questions, to figure out how much of this I need or how much of this is there, the first step in doing this is always going to be conversion to moles, right? So we're going to have a first step that is a conversion to moles. And what we're going to try to figure out here is how many moles of this lead nitrate is in this solution originally, right? So that's the first question. Now, we can answer that, right, because we do know the concentration, we know the molarity, and we know the volume. So there's a couple of different ways that we could do this. I always like to go back to just the molarity equation, right? So remember that molarity is equal to moles of solute, which our solute here would be the lead nitrate, per liters of solution, right? We know the concentration, we know the molarity for the solution, and we also know the volume that we have of it. We have the 0.15 liters, right? So these guys would be our knowns, and we would be solving for our unknowns here in moles. So if we go ahead and plug that in, we have 0.175 molar is equal to some unknown x over our volume here. We have 0.150 liters, right? So to solve for x, I'm going to multiply both sides by 0.150, multiply by 0.150. This guy cancels, and we are left here with x is equal to 0.02625 moles, and that's of PbNO3. Okay, so there's another way that you can imagine this, and it's usually not what I do, but I'm just going to go ahead and show it to you if it makes a little bit more sense. So again, we can utilize this idea of concentration as kind of like a unit equation, right? So this concentration is in terms of moles per 1 liter of solution, and that concentration tells you that there are 0.175 0.175 moles for every 1 liter of solution. So we could utilize this as a unit equation, just kind of like we do for our molar mass, right? Molar mass tells us grams for every 1 mole. This is going to tell you moles for every 1 liter. And we could kind of convert this into kind of a statement of equivalency. So this is 0.175 moles for every 1 liter. All right, so if I took my volume that I had here, so I had 0.150 liters, and I know that for every 0.175 moles, I get a liter. I could use this as a conversion, right? So for every 1 liter, there are 0.175 moles. So when I multiply, the liters cancel and I end up in terms of moles. And again, you do the exact same thing overall. You take the concentration and you multiply by the volume. Oh, pardon me. You take the volume and you multiply by the concentration. That's exactly what we did up here to solve for the same thing. But this is just kind of looking at it in a different way. It's looking at molarity as a unit conversion as opposed to like a known equation to solve. All right, so when you do that, you get the same number out. It ends up being 0.02625 moles of PbNO3. Okay, so that's step number 1. Step number 2, we're going to convert to moles of whatever we're solving for of our unknown. This ends up being KCl. Right, so the question here we had was, how much KCl do we use to completely react with this amount of lead nitrate? And so now we know our moles of lead nitrate. We're going to utilize that to convert to moles of KCl that we need. So 0.02625 moles of PbNO3. Now we're going to utilize those numbers in the balanced chemical equation, right? So we go back up here. For every 1 of these guys, we need 2 of these guys, right? We're trying to convert 2 moles of KCl, and we're coming from moles of PbNO3. So for every 1 mole of PbNO3, we need 2 moles of KCl. So essentially, we have to double the number of moles of the PbNO3. And when we do that, that gives us a 0.0525 moles of KCl. So this is how much we need to completely react with the lead nitrate. And so then finally, in 3, once we know moles, we're going to convert to from moles of whatever we're dealing with to whatever they're asking us. And this tends to usually be a volume, right? So they specifically want to know what volume of this 0.15 molar solution do we need to get us this amount of moles. And so we're going to essentially kind of do that first step that we did in reverse, right? That KCl solution had a molarity of 0.150. Now we know the number of moles that we need, right? So that's going to go on top. Oops, ugly. 525 moles of KCl. And we're going to be solving for this volume underneath. So to do that, I would multiply the x across, and then I would end up redividing by the 0.015. So x here ends up being 0.0525 moles divided by the 0.150 molar. That ends up giving me a volume here of 0.350 liters. And again, if you wanted to convert this, this is 350 milliliters. So it's the exact same type of problems, right? We could have asked how much of this guy do we make or how much of this guy do we make. Again, it's just we're coming in a different way, right? To get to moles, instead of using molar mass, we have to use this idea behind molarity and the solution concentrations to first convert to moles. Once we're in moles, this step is the exact same, so you don't have to worry about that. And then usually we have to come back out in terms of solving for a volume needed or a concentration needed, etc. Okay. Okay, so go ahead and try this one on your own. So in this problem, We've got a nitric acid solution. They give us a concentration of it. So we have 0.150 molar. And they want to know what volume of it, so the volume is the question here, will completely react with a sodium carbonate solution that has a concentration of 0.108 molar, and specifically we only have 35.7 milliliters of this. So it's a very similar question. The only thing I would note before you guys get started is they give us this, our volume in milliliters, but just as a reminder, molarity is defined in terms of moles per liter, right? So if you're wanting to solve for moles, you can't utilize milliliters in the molarity equation. You have to convert to liters first. So go ahead and give this one a shot, and then come back for the answer. Pause the video, and then come back for the answer. Okay, so hopefully you guys got an answer. So the answer for this guy ends up being, again, we're looking for the volume of nitric acid required to completely react with the given amount of sodium carbonate, and hopefully you guys got that volume to be 0.0514 liters, or again, you can convert this to milliliters, and this ends up being 51.4 milliliters. Okay, so I'll go ahead and go through how I got that. Again, we're wanting to figure out how much of this is needed to completely react with a given amount of our sodium carbonate. And the amount of our sodium carbonate is given to us by the concentration and the volume, right? So the first step is always going to be conversion to moles. So I'm just going to go ahead and use the fact that we have the concentration, we've got the molarity. So this is our concentration. We know what volume we're using of it, right? So concentration is equal to moles per liter. This needs to be converted to liters first. And so I'm going to do that. I'm just going to divide by 1,000. So that just moves the decimal 3 places to the left. So this ends up being 0.0357 liters. And again, what we're solving for here is the number of moles. So we'll just act like this is some unknown value that we're going to solve for. So to do that, we're going to multiply our concentration by our volume, and when we do that, we end up with a number that is pretty small. So we have 3.86 times 10 to the minus 3 moles, and this is of our sodium carbonate. So that's number one, is getting to moles, right? Once we're in moles, we can now utilize those numbers to convert to moles of whatever we're wanting to know about, right? So we wanted to know about how much of this guy we needed to completely react. So we know our moles of sodium carbonate. For every 1 sodium carbonate, we need to utilize 2 HNO3, so 2 nitric acids, right? So our 1 mole of sodium carbonate is on bottom in Na2CO3. For every 2 moles of HNO3, again, the moles of sodium carbonate cancel. We'll take our 3.86 times 10 to the minus 3, multiply by 2, we'll double it, and that gives us a number of moles of 7.71 times 10 to the minus 3, and that's in terms of moles of HNO3. Okay, so we have moles of HNO3. This last step, we're going to come out of this by converting from moles of whatever it is to volume, given the fact that we do know the concentration of this solution. Okay, so again, concentration is 0.150 molar. We now know the number of moles we need, so we know the number on top is 7.71 times 10 to the minus 3. And what we're going to solve for is this unknown volume on bottom, right? So to solve for this, I'm going to multiply both sides by x. That's going to give me a 0.150 times x is equal to 7.71 times 10 to the minus 3. Now to solve for x, we're just going to divide both sides by 0.150. Divide both sides by 0.150. and that gives us an X equal to a 0.0514 liters, because again, we're solving for a volume. And if you wanted to convert this to milliliters, you would just move the decimal 1, 2, 3 places to the right. So this would give you 51.4 milliliters. I do that whole conversion between liters and milliliters thing because if you guys remember being in the lab, a lot of the volumes that we measure are actually in milliliters. So a liter's kind of big. We don't usually utilize that much of stuff. And so we're usually dealing with things in milliliters, but you do have to be able to convert back and forth between the two. Okay, so the last kind of topic that we're going to talk about with respect to the solution stoichiometry stuff is going to deal with something called titrations. So titration is a technique that we utilize quite a bit with respect to general chemistry. The idea behind a titration, the main goal behind it is to essentially allow us a means by which we can determine the concentration of an unknown solution given that we know the concentration of another solution, right? So we're going to take a known, and that's going to allow us to determine the concentration of an unknown. Okay, so in a titration, we use a specialized little piece of equipment that is called a burette. So this is what a burette would look like. It's actually fairly large. It's kind of a small picture. But in the lab, this would be kind of like, I don't know, if you think about how tall I am, and you know how tall I am, this would like probably be half of my body, right? I would say this is maybe like, 2.5 feet, 3 feet tall, right? And so what happens in the lab is we set this guy up. It's got very, very, very precise volume markings, right? So it has these nice volume markings. So it's kind of like a really fairly analytical graduated cylinder, right? We can measure volume really accurately with respect to this burette. Okay, so usually what we'll put in here is the known. Usually the known is called the titrant. And then what happens is we'll have a reaction occurring where we're releasing this solution into something else, and we control that via this little guy right here. This is something called a stopcock, right? So when this guy is parallel, right, which is what it is right now, it's parallel. That means it's open, right? And so liquid is allowed to flow from it when it is perpendicular. So when it's perpendicular, it is closed, and that is going to stop the flow of any type of solution from the burette, okay? Okay, so very commonly, the most at least common type of titration that we deal with in 151 as well as 152 are acid-base titrations, right? So in an acid-base titration, usually what we're trying to do is again determine the concentration of an unknown solution, and that can either be an acid or a base that has an unknown concentration, utilizing a neutralization reaction. So a neutralization reaction with a known, right? So for example, let's say that we had an unknown solution of sodium hydroxide. So just a reminder, sodium hydroxide is a base. It's a strong base. We don't know its concentration, but what we do know, what we'll have as a known, is the concentration, let's say, of an acid that it's going to react with. So our known at this point in time would be something like HCl or nitric acid or some very strong acid. Okay, so again, we're going to utilize this neutralization reaction to allow us to know our known and determine the concentration of our unknown. And just as a reminder, the net ionic equation of a neutralization reaction is just hydronium ions or protons or hydrogen plus H plus hydroxide going to make water, okay? So now what happens, right? So we're going to have our unknown, we're going to add it to our known or vice versa, and we're going to add something that's called a chemical indicator. And so the idea behind this is that this chemical indicator, we're going to see a color change, right? So we're going to see a color change when we reach what is called the equivalence point or the end point in a titration, okay? So the equivalence point, and frequently I will abbreviate this EQ, and then PT, I write that all the time. So just note that if you see this, I'm referring to the equivalence point. It is defined as the point in time of the titration where the number of moles of acid, or H plus, equal the number of moles of base, or OH minus. Okay, so again, and I'm going to set this up in a second to kind of visualize what's actually happening here, but this indicator is essentially going to allow us to determine when we reach this stage in the titration. And again, what we'll see is something go from a clear solution, so no color at all, and then at the end point or the equivalence point of the titration, usually we'll see something turn pink, because very frequently the indicator that we use turns pink when we reach that end point in the titration. Okay, so again, what will happen is we'll have, let's say, an unknown. So let's say that our acid is the unknown in this situation, and our acid's going to be in something called an Erlenmeyer flask. So hopefully you guys remember what an Erlenmeyer flask is. We don't know what the concentration is of this, right? But let's say that we're doing this titration, right? And we do know the concentration of the base that we're adding to it, and the base can be sodium hydroxide up here, right? So we can measure the volume of our burette. We know the concentration of this guy. And so what that's going to allow us to do is determine the actual number of molecules that we are letting flow through in this overall titration, okay? So let's say that we didn't know how many molecules of acid were in here originally, but we did have a means by which we could determine the number of molecules of base that we have released from our burette. Okay, so let's say that we open the stopcock, right, and we let the base flow from the burette into our little Erlenmeyer to react with the acid. For every one molecule of our H plus, we're going to need one molecule of our OH minus, given our acid-base reaction, given our neutralization reaction. And so we let this guy flow until the solution turns pink, which again tells us that we are at the equivalence point in the titration. And as a reminder, at the equivalence point, the number of molecules or the number of moles of H plus equal the number of moles of OH minus, right? So again, we let this guy flow through until it turns pink. We then shut it off, right? So we turn it back to perpendicular and we read the volume markings so that we can determine the actual numbers of molecules or moles of OH minus that we've released, and then utilize that data to figure out how many moles or molecules of H plus were there originally, okay? Okay, so let's actually go through an example here to get you a better idea, and then I'll let you guys do a problem on your own. Okay, so I'm going to go ahead and draw out a titration setup over here on the left. So in this titration, we have an acid, and that acid is HCl. And we're going to have our acid in our little Erlenmeyer flask underneath our burette, right? So this guy is our acid. It's HCl again. And there's a couple things that we do know about this, right? So we can go and draw a little level of liquid. We know the volume that was there, or the volume of the acid that we put in to our flask. It ends up being, 10. Sorry, wrong one. This guy ends up being 10 milliliters. We know it's HCl, but what we don't know right now is the concentration. So this is going to be the thing that we're trying to figure out, right? What is the concentration of this HCl solution, okay? We are titrating it with sodium hydroxide. So I can draw my burette, my little stopcock here. Again, this guy is going to be our sodium hydroxide solution. We do know a lot more about this, right? So what this little problem tells us is that the concentration of the sodium hydroxide is 0.1 molar, right? And then what they tell us is in this titration, to get to the equivalence point, we use 12 mils. So the reality of this, how this is usually set up is at the very top of the flask, or the very top of the burette, we measure this as being 0 milliliters. So we had put our sodium hydroxide solution into our burette before we started. We had added our indicator, right? So we put the indicator in. Again, it's just going to be a solution. And then we had opened this, right? So we had recorded this. This is what we would call volume initial. We had opened this and allowed this guy to flow in, okay? And so we allowed to flow in, until this solution turns pink, right? And so at that point in time, we would then close it, right? And we would read the final volume, okay? So because this guy reads from the top down, so it would be 0. What we would read here at this final volume, so we'd call this V final, this would end up being about 12 mils, right? So that's what we measure from our burette, okay? Okay, so for the sodium hydroxide, when we use this burette, what we're really trying to calculate or determine is the change in volume from the final volume and the initial volume. So just as a note, this guy, our little triangle, is the Greek letter delta. This means change in. And change in is always final minus initial, right? So the change in volume would be the volume final minus the volume initial. And so for this guy, we would have a final volume of 12 mils minus an initial volume of 0 mils. That would give us a delta V, or a change in volume, of 12 milliliters. Okay, so it allowed us, or it took 12 milliliters of this 0.1 molar sodium hydroxide solution to get to the equivalence point. Okay, so then what are we going to do with that? How are we going to utilize that data to determine the concentration? So at the equivalence point, the number of moles of acid equal the number of moles of base, right? And so we can say base. I'm going to go ahead and write out a hydroxide ion, but just note I'm saying base here, and I'm saying acid over here. Okay, so again, that's at the endpoint, the equivalence point of titration. I can determine one of these values right now, right? So for the sodium hydroxide, for the base, I knew the concentration, right? I also knew the volume that was required to get me to the equivalence point. Okay, so just as a reminder, molarity is equal to moles per liter. I know the concentration, I know the volume, so I can utilize that to calculate the number of moles at the equivalence point. How many moles of sodium hydroxide have I released, okay? So I'll go ahead and I'll take that 0.100 molar of NaOH. That's going to be equal to this unknown moles divided by the volume, but again, that volume has to be in liters, and right now that change in volume is in milliliters. So I'm just going to move the decimal place 1, 2, 3 places to the left, and this converts to 0.012 liters, and I can go ahead and plug that in. All right, and so then when I multiply the concentration times the volume, that's how I'm going to solve for X. And that's going to end up being as 0.0012 moles of NaOH. Okay, so again, that's how many moles we have released of the sodium hydroxide to get to the equivalence point. We also know at the equivalence point, that is equal to the number of moles of H+ that were initially in that flask, right? So this X is also equal to the number of moles of acid, or H+, which is, again, numerically equivalent to what we just calculated at the equivalence point. So this is 0.0012 moles of HCl, okay? Okay, so now the whole purpose of this is determining the concentration of HCl, right? We now know how many moles were there, right? Because that was the same as the number of moles that were required to get to the equivalence point. To calculate the concentration, right? All we need, if we know this guy, now we just need to know what the volume was of that guy initially, right? And again, this was known, okay? So to calculate the concentration of our HCl, or the molarity, we have the number of moles, 0.0012 moles of HCl. Now we just need to divide that by the volume that was there initially in liters, right? So again, we're going to move the decimal 3 places to the left. This ends up being 0.0100 liters. So 0.0100 liters. And when we take that guy, we multiply or divide by the 0.01, we end up with a concentration of 0.120 molar HCl. Okay, so again, this is a good illustration of how you would utilize an acid-base titration. You have an unknown. That unknown is the concentration of HCl. You know the volume that you use of it, right? And you're going to titrate it with a known solution, right, that has a known concentration. So we're going to titrate it with the sodium hydroxide solution. Again, you're going to add volume until it reaches the equivalence point, and at that point in time, you're going to be able to calculate, given the accuracy of the burette, how much volume you had to release to get it to that equivalence point. The concentration coupled with the volume data will tell you the number of moles. That will tell you that the number of moles that were actually in the acid initially, and they will divide by the volume of that acid to get the overall concentration of the HCl or your acid. Okay, so go ahead and try this one. Again, give it a shot, pause the video, come back and determine the answer, or I'll show you the answer, and then I think we are done with this overall video. So go ahead and give it a shot, pause it, and then come back. Okay, so we'll go ahead and go over this. So I've gone ahead and drawn a little setup here where we have our burette. This time it's kind of reverse of what we saw the last time. So now the unknown is the base, right? So our base here is potassium hydroxide. Our known is the acid. The acid is HCl. And so, again, what is known about this acid solution? Well, we know the concentration of it, right? So we know the concentration of the HCl. We don't know the concentration of the potassium hydroxide, but we're going to utilize the HCl as well as this acid-base titration to figure out the concentration of the potassium hydroxide, okay? So again, we've got our potassium hydroxide in our little Erlenmeyer flask. We know the volume of it that is there. And now we're going to take our HCl solution. Its volume initial is going to be at the very top of the burette, which is 0.00 mils, right? And so now we're going to open this guy. We're going to open. This guy is going to flow down through it, right? So we're going to see this guy go down until the point in time where we reach the end point. We get a pink color turn. It stays that way. So then we will close this and we will read the volume final. And so for this guy, the final volume was 41.00 milliliters. Okay, so a lot of it had to flow through to actually reach the equivalence point in this titration. Okay, so now how are we going to utilize that data, right? So again, at the equivalence point, the number of moles of HCl equal the number of moles of potassium hydroxide. So number of moles of acid equal number of moles of base, okay? Which one can we figure out, right? So we know the concentration, the molarity of the HCl. We also know the volume that we were required to use of it to get us to this equivalence point, right? So this change in volume here is volume final minus volume initial. Change in volume is 41 minus 0, which is 41 milliliters, right? Okay, so again, with respect to molarity, we have to convert this to liters. We're going to move the decimal 3 places to the left, and we have a volume of 0.041 liters, okay? Now, if the concentration is 0.250 molar, then we need to take the volume, we need to multiply it by the concentration to solve for this unknown number of moles, okay? So when we do that, we end up getting an X equal to a, 0, oh, no, nope, don't want that, a 0.01025 moles of HCl, right? So that's the number of moles of acid that were required to get us to equivalence point. We know that at the equivalence point, this is numerically equivalent to the number of moles of base that were there, right? So this also equals number of moles of KOH, moles of KOH. Now, to calculate the concentration, the molarity, we know that's the number of moles of whatever divided by the volume of the solution. We now know the number of moles that were there, moles, and we know the volume of the solution that was initially present, which is the 20 mils that we put into that Erlenmeyer flask. So we're going to take this guy, divide by 20, convert it to liters, which is 0.020. So this is 0.020. And we end up with a concentration of KOH, a molarity equal to a 0.513 molar KOH solution. Okay, so we're going to deal with this in the online lab that we're going to do. So you guys will get a bunch of experience doing these types of calculation, determining the concentration of an unknown base or an unknown acid given a known concentration of the other.